So just to sort of complete this top-level picture, I want to say a little bit about STG and C-, and then that'll be enough for our top-level overview. And notice I haven't actually said anything about how the type checker works inside, or how the renamer works inside, or how any of the simplifier works inside. So actually all of these are things which probably it'll be tomorrow by the time we talk about them, but go to the suggestions page to say which of these you would like to talk about in more detail, if any. Right? So, because when I said that once you've understood the data type, everything else is obvious, that wasn't quite true. So a little bit about the STG language and C language. Oh, and but just while we're here, let me remark that under this compiling one module, we have written a few notes about a little bit more detail about some of these passes, along with references to papers that describe them, where they are. So this is still something we can read. Now, how did I? So how should we think about this STG language? So STG stands for the Spineless Tagless G-machine, and dates back to a paper called, which we should refer to here. Paper pointed here to, it's the compiling lazy functional languages using stock hardware. It's quite an old paper, but it still pretty much describes the way the STG language works. But I have now come to, I used to think of STG as something very distinct, and I've now come to think of it as a kind of specialized version of core. So the process of going from core to core prep, like that preparation pass, gets core into the form in which it satisfies a number of invariants, which I've written out here. I'm not sure that I've got them all, but this would be a good place to add new ones as we find them. And then it goes from the core, this core with invariants to STG. Why do we change data type? It's because in the STG data type, we get the opportunity to add lots of other redundant information, like what are the three variables of this sub-expression? And is this a let-no escape? The result of some analyses, is this a constant, what other constant applicative forms does this thing refer to? We get to decorate the tree with the results of some simple analyses that are important for the code generator. So having a general mechanism for decorating the tree in core would have been much more awkward. So it's easier to have yet another data type, and that's what the STG syntax is. It used to be more difficult to core than it is now. The other thing to say is that on the way to STG, we drop a lot of type information. So core is fully typed. Big lambdas, little lambdas, everything has to fit together exactly. In STG, we drop most of the polymorphism information and just leave things like, which type constructor is this case expression scrutinizing? Right? So much more limited information. The core program has the property that if it passes lint, it should not core dump when you run it. So it may not do what your original Haskell program did, right, because you might have screwed up the transformation, but it should not segfault. In STG, that's not true. There's no type checker for STG that carries that guarantee. But we do much less at the STG level anyway, so it doesn't matter so much. There is an STG lint pass, but I'm not sure it even works. I'm not sure what it does anymore. So another project would be to fettle it up as a, do whatever consistency checking you can do on STG with the STG lint pass. But I suspect it's bitplotted a lot. Okay. So here are the invariants, and what are the main things that are attached are three variables, references to top-level three variables, and live variables. So let me and let no escapes. Let me just very briefly say what this means. So in the STG language, if you look at STG sim, you'll see all this stuff. I didn't put in line any definitions this time, but I'll draw a typical one. So there's an STG let form, which has a, I think it's, oh dear, something like STG RHS closure, I think, or something, and STG export. So this is the STG export type. And there's a whole bunch of other things. So this is the binding for an STG closure. Oh dear. I think there must be an ID in here somewhere that binds it. Anyway, this guy here, what's the right-hand side? So maybe I should write it in concrete syntax. So this is something like let x equal in. And what's this? This is always has one or more lambdas. No, x1 to xn. And then it has some expression here. And the number of lambdas can be 0, but this is the only place that lambdas can be. So STG has a very strong operational model. Let means allocate, and that's the only place that allocation occurs except when you're returning values. But let always means allocate. So every let allocates one heap object for each let binding. And this guy means allocate the heap object that looks like this. It has some code. I'm going to tell you more about heap representations. Code. And what are these guys? These guys are the free variables of this whole right-hand side. Right? So what are the free variables? Well, we need to know exactly what they are and in what order. And so that information is attached in this STG RHS closure type. During this core to STG pass, we do the free variable analysis, make a list of the free variables and attach it to the tree. So there's a sort of single canonical place where we nail down exactly what this heap object will look like. So that's good for the locally bound free variables, like if there was a lambda y here, and if there was y mentioned, then y would be in here. But inside here, you might call some function f. Now, does f, what about f? F is a top-level constant, so it doesn't need to be put in this closure, because in the code, we can just call f by using a global. You know, we'd say jump to f underscore closure, and that's its top-level name. So maybe we don't need to mention f at all. But there is a worry, because f might be or might refer to a constant duplicative form. So if you, and that means something like this, if you say x is from 3, so this is a top-level definition in the module. X is of type list of int. So this is the infinite list of integers starting at 3. So anybody who uses X is going to make this, is going to start evaluating this infinite list as far as they need it. But the next person who evaluates it, you probably don't expect it to re-evaluate it, you expect it to be hung on to. So the danger is that you hang on to all these top-level data structures, which might get to be arbitrarily big, and you hang on to them all until the end of the program. And that's what we used to do. We used to just hang on to them all until the end of the program. These are called constant duplicative forms, and they're a huge pain. If you hang on to them all to the end of the program, then it's not difficult to make program transformations that make your space behavior much worse, because turning something from a local definition, in which case it's hung on to in a kind of explicit way, to a global one means it's hung on to forever. And that can make the space behavior of a program be a disaster. So instead, well, one alternative would be to say, oh, well, maybe this f thing, well, if we mention, let me call this p. If we mention p in here, perhaps we should point to p as one of the free variables. We say, oh, p is one of these constant duplicative form things. So we'll put it in here. We won't keep onto it forever. The only way it gets hung onto is by this pointer. That's the only thing that keeps the infinite structure alive. Oh, but that's not so good, because other people might refer to p by name, and then they wouldn't get the benefit of your evaluation. And worse still, what if it didn't mention p explicitly? What if f mentioned p? F might be a perfectly ordinary function, fx equals something, but it mentions p. So if you can call f, then you can use p, and that should keep p alive. So in effect, we need a way to say, when should p be kept alive? Well, the answer is, if any code that could still execute in the lifetime of the rest of this program can use p, then p should be kept alive. So we need a reachability thing that covers code as well as heap allocated data. So in effect, in this code here, for the right-hand side of this thumb, we need to say, oh, so in here, we're going to mention f, or some label involving f, like f, you know, entry 7, or some funny label involving f. That's what's going to be in the machine code. And so we want something beside the machine code that we call the static reference table that contains pointers to the things that are mentioned in the code. Right? That's the static reference table. And you should think of it as being very like the dynamic reference table, that is the environment captured in the dynamically allocated object, but we don't allocate it dynamically because that takes instructions, we just allocate it statically. And then the garbage collector, when it says, oh, this thing is alive, it follows these pointers and it follows these pointers. Does that make sense? So I think it's worth just knowing that much about what static reference tables are.
You use the other technique that you mentioned for things that are floated up that aren't really global, right? Things that are not really global but are...
Things that are floated up get treated by this exact technique. We don't so we don't retain the fact that they were originally local. We just use this game. Actually, well, maybe you could do this game for those guys, but we don't. Yeah.
I just want to be sure I understand the problem. So you have this constant applicative form. You have a pointer to this allocated as part of initialized data.
Yep.
And,
yep. Here it is.
And
initialized data. Yep.
And the garbage collector needs to know when it's safe to collect the things that that point to.
Right.
But it's not a root forever. It's not a part of the heap. And instead, you decide when that is reachable by following the static reference tables.
Yes, that's right. Following essentially the transitive closure of all the code that could yet be executed to see which constant applicative forms. So the idea is they die as soon as they can no longer be reached, which is what garbage collectors are supposed to do.
Okay, so if you see something on the stack, it has a static reference table, you follow.
Absolutely, yeah. Yeah. So it sort of extends the whole garbage collection marking phase to code references as well as dynamic heap references. And this was a big exercise putting this in the first place. But since then, we had so many little hoops that we were trying to jump through to try to avoid this problem that just biting the bullet turned out to make things up. Okay, so that's STG. The only other thing to say about the STG language is about let no escape. So let me just say briefly what those mean, so that if you trip across them, you know, and you can ask to find out more about them. So here's a common pattern. Let f be lambda f in case y of, and then some constructor f3, some other constructor return the emptiness, some third constructor f7. Right. So now think how this will execute it left to itself. What might happen is I said let allocates. So just left to itself, you'll allocate a function closure in the heap. And then at this point here, you'll jump to that function closure, passing it 3, and here you jump to the function closure, passing it 7. But what's really going on is that we've got a kind of downward control flow. We've got y. If we were drawing a flow graph, we might write this. Y, and then either, if it's A or it's sort of C, then go to do this F stuff, this block here, and otherwise return the emptiness. Right? So this is playing more the role of a control point than a fully fledged data structure, right? So we say it doesn't escape because if you follow the completely strict control flow through this case expression, this heap allocated object, if it was heap allocated, would never would die before the stack retreated. Give it a rather operational description. So when I come here, what I'd really like to do is to jump to a particular code label, F entry or something, with 3 in a register to say that's, jump to this code point and jump to this join point passing 3, jump to this code point passing 7. And this is the only difference between, these encapsulate the differences between these 2 points. So during the call to STG class, we do a little analysis that turns that instead of using a let constructor, it uses a let no escape constructor, and the semantics of the let no escape constructor, semantically it's just like a let, but operationally it does no heap allocation. Instead, it maybe does a little stack allocation to make sure that the environment is on the stack. And then these calls, things that look like calls, turn into a jump and adjust the stack pointer. And this pattern, you might think, is this worth doing? This pattern occurs a lot. Definitely worth doing. The case-of-case transformation, which is described in a paper that I point to from this overview, generates a lot of these join points. So it's quite worth doing. But we don't remember how the lets came into being, which is generate lets like crazy, and let the analysis discover which ones are let no escape things. Did you have a question?
Oh, this is sort of reminds me of tail call elimination.
It's not quite like tail call elimination because a tail call would just says you deallocate the current stack frame and jump. So all calls in GHC really are not all calls. all calls that are tail calls are done with a tail call elimination, but they may be to unknown functions elsewhere. This is to a known function that's effectively whose environment is on the stack already. So it's like a very specialized version of tail call. But it's very hard to practice. Okay. So that's let no escape and roughly what it means. But not formalized. This let no escape thing is accompanied with an analysis to figure out which live variables are and what the stack should look like and so forth. But I've never written a paper about that or made any kind of formal description or proofs about it. So there's another project, not a hacking project, but a kind of retrospective engineering project to try to formalize what GHC does at that point. We've never written about it or described it in any formal way. Yeah.
So I guess I don't understand the motivation of translating once again to STG. I mean, you just talked about the core that you're so proud of. Why can't you do it?
Why couldn't the code generator just work off core?
Right.
Good. So the reason is the following, that the code generator, when it is, for example, dealing with a let, needs to say what, needs to know what the free variables are. Let's take the simplest possible thing. Or needs to know, is this let, take a slightly more complicated one, is this let a let no escape? Do I need to allocate a heap object for this, or can I do this clever jumping and stack adjusting thing? Right? How would it know?
Okay.
Well, you look at the program and you look at the way in which fail is used. So you do a little analysis of the program. Right? So STG is simply core in this that obeys these invariants about where lambdas can be in any form, plus the results of the analysis decorating the tree. So it has all the pieces in place, ready for the code generator. And the code generator is already extremely complicated, much too complicated. It needs factoring into two. But if you added these other things as well, it would be unmanageable. So it's really just decoration with the results of analysis. But having a way for adding that decoration to core, or for enforcing the invariance in core, would place more constraints on core that wouldn't be relevant to the earlier factors. Does that? I guess that's why.